right, so I think I'm ready. Hopefully you're ready as well. So the idea today is that up to now, we've been dealing with these oil droplets in these Millikan experiments. So Millikan had charges suspended between the electric plates, and this meant that the forces were balanced. That's what we've done so far, right? The forces. The forces were balanced. Which means that the electric force, which is up, Zane, you follow along? And the weight force down were equal and opposite, I guess, right? Okay. So now the big question is, what happens if they're not balanced?
You'll accelerate one way.
Accelerate one way or the other, right? This is in fact really no different than if I just take this. Oh.
Oh, that's a force there.
Can't you just highlight the whole thing?
Jeez. If I take the whole thing and do this, and now really we're talking about what?
And apply.
Yeah, applied force and friction. So really, it is exactly the same thing, just different names of the forces, and it's up and down. Right, Sarah? Are you following? Okay. So I want to make that perfectly clear that it's literally something that you've pretty much done already. Right? Yeah. Okay, so if the forces are not balanced, there will be a net force on the charge causing the acceleration. I don't know why it says unbalanced or F net, I guess. If it's not balanced, that means that the forces are unbalanced, and there is a net force that is greater than zero, right? It looks like I was trying to explain that right there, that same thing, right? So one of these looks like, is the bottom one bigger here? Let's make it obviously bigger. Okay, so in this particular case here, the weight force is substantially more, which means it's going to accelerate down. You could even tell me, if you stop and think about it, what's the maximum acceleration down going to be? Minus 9.8. So like right now, we know that my answer here, if I gave you a problem to do, your answer would have to be a number that is less than 9.8, wouldn't you? If you got like 17 or 443, well, you'd be wrong. You should know that. You should go, whoa, that doesn't make sense. Right? So, using this net force and acceleration, we can solve problems for motion like fluid. In fact, not only can we solve for the acceleration, we can solve for the distance traveled and the velocity, and literally everything we've pretty much done the entire year. Weird how that happens on the very last day. Really, everything has been sort of, like, you know, we're building that cake and I'm putting the icing on right now. We're going to stick the candles in and we're going to blow them out. Except it's not going to be as much fun as birthday cake. When I was a kid, the mums used to put like nickels and quarters in the cake. Did anyone ever get that?
What?
Yeah, they used to take money and you put it in the cake before they bake it, right? And then when you got your piece of cake, then you had to dig through to see if you got any money.
When you're really hot, though.
When what?
When you're really hot.
Well, it was like they let it cool.
Yeah, you know, it comes out of the oven and you're just digging. Oh my God.
Then they realized that, you know, all these people have handled it. We're putting all those germs in the cake, and yeah, they stopped doing that. But it was a thing when I was a kid.
I feel like it's killed the kids.
Yeah. And then they started wrapping it in like plastic wrap, and that probably wasn't a good idea either. Stop thinking about it. Yeah. Let's just give everybody a quarter and forget about it. How did I get talking about that? How did that happen?
Because we're
making a cake.
Oh yeah, that's right. Jeez, I hate when I do that.
we started talking about it.
Oh yeah. Now, okay, so before we get into that, I need to sort of explain a little bit about like fields, which I normally have done already, but because I wanted to make sure I got you here, it's going to seem a little different here. So first I want you to think about a line of charge and a single point charge placed nearby. So in other words, I've got like a metal plate here, kind of like in a Millikan apparatus, and you can see that it is charged with several positive charges. And we have a single point charge down here. It could be, this one's positive, it could be an oil droplet or something like that, right? Okay, so what I need you to understand is that the horizontal components of corresponding charge will cancel and the vertical components will add. What I'm trying to say there is this, okay? This, if you want to think of it this way, this positive charge is pushing this way. Well, part of that pushing is actually sideways, right?
Yeah.
And the other part is down, right? And similarly over here, this guy over here, he pushes a little bit that way and also down, right? Well, these two are equal and opposite, so they actually do what? They cancel each other out, and the blue ones here actually add together. So you get like an increased force. Okay, so the red ones cancel out, and now would that be true for this one and this one?
Yeah.
Yes, right? So all of that horizontal kind of cancels, and all of the vertical kind of adds or increases. And in fact, if you also, and I've never really actually talked about this before, but if you sort of increase it with that negative, then that just does it all in kind of reverse, right? The attractive force is actually more down. So you really get inside an electric field, you have a really strong, inside two charged plates, you have a really strong electric field. How do you know it's really strong? Because the field lines are close together. Close together. Okay? Does that kind of make sense? Yeah? Give me the nod of understanding. No, sir? Or Jordan? No?
I mean, it's kind of confusing, but we got it.
Okay. Okay, there it is right there. I guess I was thinking ahead. For oppositely charged plates, the effect is enhanced, right? Now, you should also maybe think that the field is constant, directed from positive to negative. Now, how much of that have we talked about, going from positive to negative?
That's just quick.
Have we talked about that a whole lot?
No, the grade 9 rotation.
Yeah, in the grade 9. But didn't I do like where it's like positive test? Yeah, I did do that. I remember doing positive test charge away, right?
Yeah.
Yeah, we did a little bit of that, but I should probably come back to that. The field is constant and directed from the positive to the negative plate. That is something you need to know. From positive to negative.
It's always like that.
Pardon me?
It's always like
It's
that.
always from positive to negative. And that's the deal because we use what charge for, to test it? We use a positive test charge. Scientists throughout the world have agreed we're going to use positive test charges, which means it's going to be pushed away from positive and being attracted towards negative, right? It's just a convention, just an agreement, like red lights mean stop. Now, there is a bit of a bulging on the sides. The edges of the field bulge slightly since there's no charges outside the plates to balance the horizontal effect. Like as you get farther over to the edge, over here, right, then this guy here, if this was positive, this guy here is going to push that way, but there's no corresponding one over here to push it back, right? So there's a little bit of a bulge on the side, but basically what I'm saying is don't worry about that. We're going to assume, just for simplicity's sake, that the field between the plates is constant. Okay? But technically it's a little bit weaker at the edges. Not going to worry about it. Okay? Nor do I expect, you know that I'm just sort of making sure that you don't worry about it. Okay, what's the next thing? Is it right to the sample question? Yeah, that's what I thought. Okay, give me a second here. Excellent. Okay, so, and again I find it's the reading that really messes kids up. I know you think it's weird, but reading it aloud actually helps. Yeah, you should put that away, because I'm doing the helping here, right? Doing the teaching. Okay. A 1.0 times 10 to the minus 4 kilogram charge of 3.2 times 10 to the minus 19 coulombs. You'll notice that it never uses the word mass, does it? Does it say mass? No, you have to get that this is the mass basically from the fact that it's a kilogram. This is the mass. Yes, reading's important. A 1.0 times 10 to the minus 4 kilogram charge of 3.2 times 10 to the minus 19 coulombs, so that is our Q, is dropped into electric field. The plates are 1.5 centimeters apart. So I guess that would be a D value, right? The electric field strength is 1.0 times 10 to the 15 newtons per coulomb. That is our value for E, determine the net force on the object. We are looking for the F net. All right, so I've had a moment to think about that. What should we do first? Should we draw a picture?
Yeah.
Really?
No.
Well, I'm sorry, Sarah, but that's one of the recommended strategies is to draw a picture. It's drop-plug field, so we know that it's kind of like this, right? We know that we have a weight force down. Now, we don't actually know if we don't actually know which direction the electric field is, do we? Technically. And in hindsight, I should probably fix that. We're going to have to assume that it's opposite. Is it always going to be opposite? Only if I'm throwing a curveball at you is it going to be in the same direction. Right?
But will you state that you're throwing it?
No, but I might specifically say, the top is positive and the charge is negative, and then make you realize that that means that it's attracted, right? Like, if the top is negative and the charge is positive, well, then it's going to be up, right? They have to be opposite, right? I guess I could ask you, what would the top have to be if this is positive for it to be suspended, right? I would expect you to be able to figure that out. Yeah, gravity for sure is always down. Yeah. Okay, so determine the net force in the object. Can you find the weight force, Jordan? Yes. How do we do that? Fw is equal to mg, right? My mass is this number right here. 1.0 times 10 to the minus 4. We're going to multiply by minus 9.8. Oh, this is going to be 9.8, isn't it? As I want. So that's going to be minus 9.8, I think, times 10 to the minus 3. Am I right?
4.
To the minus 4? Oh, yeah, right. Okay.
How come you didn't use like the Q, the E equals F?
I just haven't got to yet.
No, I know, but I used that first.
Oh, you can do that first. There's a couple of steps here that doesn't really matter what order you do. I'll do the next one and then I'll have that discussion, okay? I think I hear what you're saying. How do we find the FE? Well, we know that E is equal to FE over Q. And our electric field strength is 1 times 10 to the 15. We're solving for FE. The Q value is, now you'll have to note that it's in what? Coulombs. So if this is in coulombs, this is in Newton per coulomb, they have to both be the same, right? If this is newtons per coulomb and this is Elches, what do? Convert it.
Why?
Because it says newtons per coulomb. Right? It's got to be in coulombs. So this number down here is going to be my Q, 3.2 times 10. I gotta do this thing. Hang on. Okay. So that gives us that the FE is, multiply those together, and you get 3.2 times 10 to the minus 4. I'll pause there for a second. 3.2 times 10 to the minus 4. That would be newtons. They'd be both of these would be newtons, right? They're both forces. Now, Leo asked, how come we didn't do that step first? That's what you're asking, right, Leo?
Oh, now I understand because it's not falling.
Well, this one is a force down.
I mean, going up.
This is a force up. But maybe you weren't asking that question, but I want you to ask it. Could I do this step first? These are independent of each other, right? Like this number here doesn't carry over, does it, right? These are two independent things. You're trying to find the force down and the force up. What I'm trying to say is it doesn't matter what order you do them in. Okay? Because they're independent. Now determine the net force. How do you find the net force? What does net force mean? It means add up all the forces. do they have to be in the same line? Like, do they have to be like both up and down? Yes, you can't have them perpendicular. Then you got to use Pythagoras. So we've got, now nobody likes to have the negative out front, so we're going to put 3.2 times 10 to the minus 4, and we're going to subtract, actually no, we're not. We're going to add a negative. Right? And so you get a net force of minus 6.6 times 10 to the minus 4 newtons. Yeah, well, I mean, I've started off with the easy one, right? Yeah. Okay, so based on that, which direction is it accelerating? Sorry, which direction, down or up or down? How come down? Because it's negative, exactly. Right? Notice one thing. What did I not do? No, that's not a density, that's a displacement. Does the distance that these things are apart matter? Doesn't appear to, right? Not so far anyways, right? Just sort of an extra number that's thrown in there. Well. Okay, so how much would that be worth? 3. Okay. So let's read this question, and as always, it's just going to sort of add on some steps. A 4.5 times 10 to the minus 6 kilogram charge, again, that's our mass, of 9.2 times 10 to the minus 15 coulombs, that's our charge, is dropped in an electric field. The electric field strength is 3.2 times 10 to the 9, that is our E. Determine the net acceleration. Oh, so we're not looking for the net force, we're looking for the acceleration. Then we're also being asked how fast is it traveling. Well, this is just a big review of the first unit.
Yeah.
Yeah, all you have is one more step.
What's that?
One more step.
For that, and then it goes with past that, right? Yeah. Is your question different? Did I do something?
No,
Okay.
I'm just saying, like, from the first.
Yeah. And that's kind of how I do things, right? Just keep adding steps. Okay, so let's draw the confusing picture.
Why draw?
Should they be balanced?
No.
No, but they shouldn't because it says there's an acceleration. But to be honest, we don't know which one is bigger to do it, right? So we might have to come back and adjust it after. Okay. Just to show you it doesn't matter what order you do them in, let's do the electric field first. So E is equal to Fe over Q. The field strength is 3.2 times 10 to the 9. Solve for Fe. The charge is 9.2 times 10 to, I'm assuming that's negative 15, is it not? Yeah. You're going to multiply. You have to be able to solve that without thinking now. You have to know what to do there. There should be no questions about that. 2.94 times 10 to the minus 5. Okay, so we've just done the electric field force. What's the other one we have to do? Got to find the up and down. We're going to find the FW, mass times gravity. Mass is 4.5 times 10 to the minus 6. Gravity is minus 9.8. Minus 4.41 times 10 to the minus 5 newtons. I'll pause there for a second. I'll do my attendance, and then I got a question for you. At this point, you should stop and you should look at these numbers and think for a second, because, and I'm going to use fancy words here, the order of magnitude should be the same. And when I say order of magnitude, what I mean is they should be kind of relatively the same. I.e., or in other words, the exponents should be the same. Right? Like minus 5 is going to be 0.0000294, and the other one is going to be 0.0000441. They should be relatively the same ballpark, strength. Could one be minus 4? Possibly. It's like an 8 and a 12, right? Like they're still kind of close together. 8 is not close to 108, right? But they're kind of close together. It could be like minus 6 and minus 5, or it could be like minus 4 and minus 5. If one is negative 5 and the other is plus 5, they are 10 orders of magnitude. They are a billion times apart.
So none of these do messed up.
Exactly. Okay, so this is a good spot to sort of stop and check. Are my orders of magnitude, are my exponents, do they make sense? Okay? Does that make sense, Jeff? Okay, so the next step is to find the net force, right? So we're going to find the net force by adding them together, and I neglected to do this last time. I'm going to write Fe plus Fw. Is that a new formula? No, it's just net force means add up all your forces. That's all it means. So Fe is going to be 2.94 times 10 to the minus 5.
The Fe, like, it doesn't have to be minus 6, like times 10 minus 6.
It could be, but it's minus 5 here, I think, isn't it?
What?
Minus 2 minus 9 and minus 6.
No, those numbers are right. Sir?
How do you know when to add when it's not suspending?
You add them when it's suspended too, right? I mean, but when they add up, they're going to equal to what? 0. I mean, now in these situations, you recognize that the forces are different, so you have to find the net force, right? In the previous situation, because it tells you it's suspended, you know that when added, they're going to give you 0. So you don't have to add because you know the answer. It's going to be 0.
Only if it's at Fe.
No. You're not listening. If the forces are unbalanced, Sarah, right, then what are they going to add up to? Not 0. They're unbalanced. If they are balanced, they're going to add up to 0.
It's accelerating.
If it's not 0, it's accelerating. Right.
When it's accelerating, then you add them.
Right. You're finding the net force because you don't know what it is. If they're balanced, then the net force is automatically 0. So you don't have to. You can add them if you want. What are you going to get? 0.
That's acceleration.
I guess once you check it works.
I just,
I know. I'd rather you think, though. Yeah.
It's minus 6 there.
Really?
Yeah, 9 for 2, 15, 6, not 5. Because it was...
Yeah, but you're right, but when you take 3.2 times 9, you're going to get 18, so you get one more.
Oh.
They're doing exponent laws, is what they're doing. They're going 9, and minus 15 should be minus 6. Yeah, they're using exponent laws, which wouldn't be a bad thing for you guys to learn about that. You do know it, you just don't realize you know it. This is going to be minus 4.41 times 10 to the minus 5. It's right, Leah, right? It's right, Trinket. Okay, so again, those exponents should be equal, and you get here now, you get a net force of negative 1.466 is what I've got, times 10 to the minus 5. If you get it slightly off here, that's okay. I'm looking for steps. I don't care about I do care, but not as much. And that's going to be newtons, right? So really, that's as far as we went in the first sample question, right? But now I need to find the net acceleration. How do I find acceleration from this? F net is equal to ma, correct? Back to unit number 3 or so. Minus 1.466 is equal to, times 10 minus 5. The mass was 4.5. It's this number here. 4.5 times 10 to the minus 6a. How do you solve this? You have to know. Divide. You simply have to know. It's just like 10 is equal to 2a. Right? Divide both sides by 2. So you're going to divide, and you're going to get a value of minus 3.26 meters per second squared.
I don't want 3.24.
Yeah, that's close enough. It all depends on your rounding. Is that a reasonable ballpark answer? What did I say about 10 minutes ago? If it's accelerating down, it's gonna have to be negative, that's true. But it also has to be a number that is, what's the biggest value it can be going down? 9.8. So if it's going down, is this ballpark right?
Yep.
Yeah, absolutely. Right? 3.26 meters per second squared. So that's our net force, or our net acceleration, I mean. Okay, so now, how fast is it traveling after 1.5 seconds? You have to assume its initial velocity is 0. If it doesn't say, it's going to be, right? And so we're going to go A is equal to delta V over delta T. This is wonderful review for the exam. Our acceleration down, 3.26. We're solving for the change in velocity. Our time was 1.5 seconds. So our change in velocity is going to be minus 4.89 meters per second. I have 4.89. That's the change in velocity, so that means then, therefore, that what? Yeah, that's, since the initial 0, the final velocity is minus 4.89. Say again? Do you think this is going to be on the exam? Like, if I was only allowed one problem on the whole exam,
It would be long. I think this one.
Probably be the next
That's
one.
gonna be drawn.
Yeah, probably.
Probably will be the next one.
no, I would probably go with this one.
Yeah, there's not a,
Yeah, I would go with this one if I was only allowed one problem on the exam, because it really covers just about everything. How far will it have fallen in that time? Before you can find out how far, you got to find the average.
And we're still going.
Yeah.
Whoa, that's like the line. Like, what are we trying to find? I'm confused.
Yeah, why don't we just,
Well, we've got the net acceleration. We've got how fast it's traveling. The last step here is how far will it have fallen? Distance.
distance,
Right? Distance. And before you get distance, you need to know
average velocity.
average velocity.
it's not that big.
It's just one more step. Do I need to put a negative in there? I guess. Dennis, gonna make me. I get 2.44 meters per second. And now what's the last step? Yep, exactly, Jeff. Good thing I didn't show you this problem back in like February, eh?
Probably your prime.
Yeah, you probably all would have ran for the door.
Yeah, I see where you did it now, so we dropped all that. Just stupid.
Yeah.
We get to school.
That's what thing did.
We show me this once, 12, I trust it.
So in other words, maybe I should, and yeah.
Well, 1 plus 2. What's his normal figure like? No. Yeah, he was like 1% something.
Let's not discuss that. You guys can go discuss that elsewhere. Solve by multiplying.
And we're done.
3.7 meters. Yeah, there's a fair bit of steps there. Yeah, it's a good thing I've shown you how to separate things, you know, line up your equals, use your units, write that formula,
Use pads.
all those things.
That's the one thing AJ's gonna take from this class. I write. Use a pencil.
Should you start these solutions right in the middle of the page when there's like a big, no, we should start in the top left-hand corner.
I write.
You gotta think ahead.
So you're writing in one line and don't script.
Oh, AJ, if you knew how much sleep I lose over stuff like that, it's driving. How about you guys find a partner, or on your own if you want, and why don't you try that one?
Okay.
This one's a little bit different. I'll give you a little hint. I'll get you started. Millikan observed a drop of unknown charge. Unknown charge. We don't know the Q. Accelerating at minus 2.3. So we know the acceleration. You'll also notice that it is negative, which means that it is down. He determines the mass of the droplet to be 5.3 times 10 to the minus 6. That is our mass. The electric field strength at the time was 8.28. That is our E. How many elementary charges is this? In fact, this is exactly what Millikan had to do. He wanted to know how many elementary charges. He was trying to solve for Q. Not only that, it's got to be in Elches. So you got to go backwards. You got to go from, instead of doing this, you got to start with the acceleration and work your way backwards until you get to Q.
Well, first we have to find
Right. You're right. That's not, but you can find it later too, right? It's kind of independent. So you're starting, like, you know the acceleration. So basically you're starting from where? You're starting from there, and you're going backwards. Okay, so Millikan observed a droplet of unknown charge accelerating at minus 2.3. He determined the mass of the droplet to be that, blah, 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 blah. So what are the first two things that we were given? We're given the A, and we're given the M. What can you get from M and A? F net. Right? The mass is 5.3 times 10 to the minus 6. Now, does the fact that the acceleration is negative matter? That it's negative? Yes, it matters. Because if it's negative, that means that the net force is? And it's in the direction down, right? Sarah?
Oh, I just want you to tell the answer.
4.
What?
4.
Like just 4.
4.
Oh.
4.
No.
I'm not golfing, it's 4.
Like 4.0.
Oh, okay, 4.0 if you want. That's good.
Anyone else said negative X on anything? It's not 4. I want negative.
The overall answer is 4. Let me go. Let me start. Okay, so this tells us that the net force is minus 1.219 times 10. Okay.
You caught him. It's not 4.
What is 4?
The final, like 5 steps from now, it's 4.
No, it's not.
That is.
He just wants you to wait and see.
Would you just let me go?
No,
Okay, so this, Sarah, just stay with it, Sarah. There's the net force. You'll notice that it is negative, which means it's down. Okay, now, if you're going backwards, Right? So now we've gone from the A, we've got ourselves to the F net. So now I need to find out what the electric force is, but I don't know the weight force yet, do I? So I gotta kind of do that kind of on the side.
Hello.
So I'm gonna find FW, mass times gravity. I said I was only gonna do the start, but whatever. 5.3 times 10 to the minus 6 times minus 9.8 is negative 5.194 times 10 to the minus 5. Yeah, that's okay. Again, I'm looking for steps in process. Okay? The actual numbers are secondary.
Can you explain again why it's like -6 and then -5?
Well, this is really, okay, I'll keep her going. So that's the weight force, right? Now, the net force is made up of, Jeff, are you like playing a game there or something rather? Stay with me now. Yeah, because the net force is the sum of all the forces. I have to get the FE, that's what I gotta get, right? So I'm gonna take this and I'm gonna plug it in there. The net force is made up of 1.219. And I'm just gonna put it in, I'm not gonna find it again, I'm using it. I know, but I'm gonna use it, I know what it is. Yeah, it's equal to MA, oh yeah, I didn't write that, did I? That's right. F net equals MA and F net equals add up all the forces. That is true. I know, but I'm only gonna have one that's missing here. Watch this. I'm gonna solve for FE, and the FW is gonna be plus negative 5.194 times 10 to the minus 5.
Listening on the recording, probably not.
Sarah, what do I do with this negative over here to get the FE all by itself? Add it to the other side. So FE is going to be plus 5.194 times 10 to the minus 5 minus 1.219 times 10 to the minus 5.
Mr. Bennett.
Whoa, let me finish. And you're going to get an FE of, I get 3.975.
Mr. Bennett. You know what?
What?
On the
Here?
when it's positive,
Your 5 is negative.
when it's positive,
Yeah, your 6 plus
like when
negative.
when the
Exponent?
plus 5.19,
Yeah?
it would be negative,
So you're negative 1.
but it's already negative.
Right.
It would be negative 5. It would be positive.
Okay. But it doesn't change the exponent. Is that what the confusion? Okay. Okay. Well, you're adding the forces, right? So this is plus and negative, so that's, when you take that negative to the other side, it becomes positive.
I know,
Shouldn't it
negative
actually be negative?
plus negative is negative 5.
No.
Well, I took this to the other side and became positive, and then I just took the FE and put it on the left, right? Like really, if you want, this is on the left, and then the whole thing is equal to FE, which I wrote at the start. Is that what you mean?
No, it needs to be,
I'll come by and I'll look and I'll see.
it needs to be.
I'll come back. Because I gotta get finished here.
It's not minus 5.
Yeah.
It is, this is a negative 5.
No, it's.
What?
Change the positive percentage.
This, yeah, you guys, it's the same as this. Let's go to the simple numbers, Sarah. 10 is equal to x plus negative 3. It's okay, you guys, relax.
Well, no, I thought the right answer just got negative. So
Okay, so what does x plus negative 3 mean? It means x minus 3, which means you add 3 to both sides. That's what I'm saying.
Well, why did-
Because I want you to show it as adding a negative, not just adding. Yeah. But let her understand.
It's like FA plus minus FF.
Yeah, that's all it is. Okay, so now we got our FE, and now what can we do? We're gonna go back one more step. How come, Leo? E is equal to FE over Q. And again, if you make a tiny mistake in arithmetic here, like if you solve this wrong, and you show all your steps, 4.5 out of 5. Okay, I will follow it through. Is it a lot of work to read? Yeah, it is. Show your work. It's important. Electric field strength is 8.28 times 10 to the 13.
We got 3.6 times.
It's in the question. 3.6.
Does it not say 3.6?
Oh,
Yeah, that's wrong.
your question might be wrong.
Oh, it's different than yours.
What?
Have you got a different number here?
Yeah.
Okay. I think what I've done here is,
It's 3.6.
no, that's why you didn't get 4. I changed this so that the answer makes more sense. And I neglected to make the change apparently on your sheet. I just made it on my screen.
Oh.
So
You know what already, where you said it?
I can, yeah.
No, he's kidding.
3.6.
You're gonna get some big giant number.
Yeah.
Yeah. That's why I changed it. You might have been right. I don't have the old answer here. It looks like 6.9 something? Times 10 to the 7, is that right?
Yeah.
Yeah, that's what I had. Yeah. 6.9 times 10 to the 7, yeah.
Oh,
Which is like, no, that's like 6 million Elches, 6 million electrons. Millikan wouldn't get that. He'd get a much lower number. Alright, all I've done there, change your e-value. I apologize. That was my error. Just erase.
Sam, can we have a full sheet of paper?
Full sheet, Jeff. I've said that many times. Many times have I said that. Okay, so we put our FE 3.975 times 10 to the minus 5. Solve for Q. Again, you have to know how to do here. Cross them over.
No, mine just looks wrong.
And you get, oh,
No.
I thought I was going to say 4, but you don't. You should get now 4.8 times 10 to the minus 19. If you use this value here. No, not Elches, coulombs. Not Elches, but
The
coulombs.
answer for our question is 20 times 10 to the 7.
I can't see. I erased that too well.
Ele já chega aqui negativo e já passa para aqui negativo.
Okay, last up. 1 Elch is 1.6 times 10 to the minus 19. So how many Elches is 4.8 times 10 to the minus 19? And literally all you're doing is dividing. And the answer?
Yeah, no, that is the answer.
4. There you go.
But
Oh my god.